This meeting is being recorded.
So the last characteristic that we'll look at in our NMR spectrum is that of multiplicity. So multiplicity is also referred to as the splitting pattern, and this gives us the number of peaks, or refers to the number of peaks in a given signal. So we'll start off over here. So we refer to this as a singlet, and there is a single peak shown. Like so, we have a doublet, which has 2 signals, triplet has 3 peaks, and then a quartet has 4. We go up to what's referred to as a septet here, which has 7 peaks. And then anything beyond that is generally just referred to as a multiplet. And we'll see this wording used throughout this section and into our practice problems. But how do we generate these types of patterns, and what does this splitting actually mean to us? So multiplicity, this results from magnetic effects of protons on each other. So the neighbors of your protons. So let's take a look at proton A here. And, right, so that's proton A. And then we have proton B next door. So proton B is proton A's neighbor. So we have these 2 protons, and we know that we have our external magnetic field here. And proton B can be either against the field or with the field. Even if we align A here with the field, we can still have 2 different electronic environments caused or produced by proton B. So therefore, proton A's signal will appear as a doublet because of the 2 spin states, the 2 different magnetic environments of proton B, against or with the external magnetic field. So that's why the neighbors contribute to the number of signals. So we see here again, if we're referencing proton A, there can be 3 possible environments seen for proton A, where both proton B's are against the field, with the field, or a combination of such. So this middle would just produce a third case. So now we have 3 possible environments that are produced by protons B on the signal for proton A. So proton A's signal, again, will be dependent on protons B and will appear as a triplet. So there is an equation that can be used when we talk about multiplicity to determine the number of peaks that we're going to see, or the multiplicity of our signal. So let's look at proton A here, and we say that it has 1, 2, 3 neighbors. So we will end up with 4 possible electronic environments, and you can work through all the scenarios here. So we have all against the field. The second scenario, all 3 protons are with the field, and then we can see 2 with, 1 against, or 2 against, 1 with. So that would be our third and fourth signal with these various combinations of protons B here. So as I mentioned before, there's an equation that simplifies this. So we have the number of neighbors represented by n plus 1. In this case, we have 3 neighboring protons, 3 HBs shown, plus 1 will give us a total of 4 signals, or 4 peaks rather, in our signal. And that's what we see here. We see this quartet as our signal for proton A. So when we talk about multiplicity, again, we can generalize this number of signals, or splitting pattern of our signals, dependent on the number of equivalent protons on adjacent carbons. So if we have neighbors that have a different electronic environment, right? We use that as our N. for the number of neighboring protons that are chemically equivalent, and we see that we have n plus 1 peaks produced. So again, this depends on the equivalent amount of neighbors. So you might have 3 protons that you'd say is one collective neighboring proton, and so. So let's look at the 3 key rules when we talk about splitting. So equivalent protons cannot split one another because they would resonate together. So when we do see splitting occur, it would be protons within a 2 or 3 bond distance. So if we were to look at both geminal protons, so those that are on the same carbon here are called geminal protons. So those are only, within 1, 2 bond distance to each other. And then with vicinal, or protons that are still in the vicinity of one another, but they're on adjacent carbons, these are a 1, 2, 3 bond distance from one another. So we would not see splitting occur in the signal for proton A, for example, from proton B, because they're too far apart, right? 1, 2, 3, 4 bond lengths. So again, if we have geminal or vicinal protons, we would see splitting. But if we have neighbors that are too far away, they would not contribute to that n plus 1 equation or splitting. So again, whatever neighbors we're counting, they would all be equivalent. And if we had a splitting pattern for the proton shown below here in red, this would be a little bit more complex than a simple triplet. And we'll get into why some of these more complex splitting patterns occur. But for this section, focus on those 3 key rules.